So in the previous example, I didn't discuss the code. These codes you will have it, but for the sake of understanding, and it's easy, how to do the LQR or LQT design, the way I do is basically after you define your A and B, these are the main things that you need to define. And then you need to choose a range of Q that you want to change. So let's say 10 to the negative 5 all the way to 10 to the power of 2. And then for every value of Q, you form the matrix Q, and then you run the LQR, and then you look at the eigenvalues of A minus BK. And then do the other one for Q2, and then you can plot them. So if I run this part, so it generates this figure for you that we discussed. So you increase Q up to certain point, and then you increase Q2. Okay. We'll run a few of cases like this later, so you will get to understand better. And then this is the design stage, and then after that you can run the simulation and then plot the simulation results. All right. Class 6, you are still in the DC. So let's talk about grid voltage support. Okay. Now grid voltage support basically in AC grids is what people call inertia. In DC grids we can also define inertia. However, let me explain it in AC first, because AC is really the common area that people talk about inertia. Now, in a synchronous machine, the mechanical torque that you apply to the machine minus the equivalent electrical torque is the net torque that really accelerates the machine. So this is the Newton's law. Or if you want to show it in terms of powers, you can show it in terms of powers, no problem. So what does this mean? If you really examine this equation more carefully, you see that it means PE equals PM minus J omega omega dot. In other words, the output power of the machine is not equal to the input power. There is another component that comes when the machine is speeding up or slowing down. If the machine is in a stationary domain, a stationary condition, yes. A steady state condition, P input power and output power are equal. But during the transients, when the machine is speeding up or slowing down, the output power, electrical power, is equal to this equation. There will be another component added to the mechanical or input power. And then you can imagine why this happens. Because when the machine is slowing down, there is this kinetic energy that has to go somewhere, right? When it slows down. So that also converts to electrical energy automatically. Or if it speeds up, it will absorb some kinetic energy. So it should absorb it from the electrical side. So this term, negative J omega omega dot, is, you can call it inertia power, or if it's torque, you can call it inertia torque, negative J omega dot, right? So why this is important? Because in synchronous machine, in synchronous generator only has this important property that the mechanical rotation and speed of the mechanical rotation and the frequency of the electrical voltage generated are equal, or in factor, they're different, the number of poles of the machine, so they are equal, right? So when, for instance, let's say in the power grid, there will be an additional load connected to the power grid. Load goes up. So because that load absorbs energy, the frequency of the power grid tends to go down. When the frequency tends to go down, the speed of the machine also tends to go down because they are equal. And then it will release kinetic energy to the grid. That's good. So as the grid needed more energy, now the machine supplied more energy without any control. This is inherent nature of synchronous machine. You see, this is not control, this is physics. So when the machine slows down, because there is more load on the electrical side, the machine automatically supplies power, and vice versa. If there is a load switches off, the stabilizing behavior is caused by inertia. So that's why I told you before that inertia is very important, and it has a significant role in stabilizing the power grid, a power grid that is built on large synchronous generators. So every AC power grid that we have currently. Okay, so keep that in mind. Okay. Look at this feedback loop that we started with, right? The optimal control feedback loop here, and then the limiting part, obviously, right? Now, if you manipulate this part a little bit, and it's just for the sake of coming to the point of inertia, even in this system, in this DC system, if you manipulate these blocks a little bit, you can represent the same system here in this way. Right? So this part here is one integrator multiplied into a constant K1 Vc, and the input to that is current. So you can say it is like a capacitor. So it receives the current and gives a voltage, and that voltage goes and subtracted from the grid voltage, and that will be the voltage across the inductor. So the voltage that the converter generates physically looks like coming from a capacitor. So the controller, what it does, puts a capacitor there, virtual capacitor. See, this is one thing, and some people really like this approach. We talked about virtual resistor before, and the reason we called it virtual resistors because we said if you write down the equations, you realize that it adds to the resistor. So you can do the same for the virtual capacitor, virtual inductor. So what I'm proving here is that this controller here, this integrator, and these two gains look like they are adding a virtual. This one adds a virtual resistor here, you see, K2, and this K1 adds a virtual capacitor to the system. Okay, so now we have, this is for the internal part, adds a resistor, and this is for the integrating part, adds a capacitor, right? And this is the reference current, and that's the actual current. So if you look at this system, and let's say something happens here in the grid, again, like what we said before, right? If this capacitor can respond properly to what happens here, it will give inertia, because capacitor does what? Capacitor stores energy, like kinetic, like the rotor that is rotating and stores kinetic energy. This also stores, you can say, electrical energy or static, electrical energy. So this, when it is working, it has some energy stored in it, right? And then when this voltage suddenly drops, let's say because one load switches in, so this voltage tends to go down. When this voltage tends to go down, the whole voltage across this line tends to go down. So capacitor releases energy. Okay? And vice versa. If there is a load here in this grid that disconnects, so the voltage tends to go up, then the voltage across this line tends to go up. The capacitor voltage tends to go up. The capacitor absorbs energy. So it's a stabilizing behavior. Got it? Very similar to what we got in synchronous machine. So this control that we have here is like adding inertia. However, the problem is this one. If you really do the numbers, look at the numbers, K1 and VC. K1 is coming from feedback loop, right? And then put the number K1 here, and then VC. For instance, for the system that we had, I think K1 was 10 and VC was 400 or something. The amount of this capacitor will be extremely small. So really, you cannot rely on the inertia coming from this capacitor. It's a very tiny amount of inertia. If you want to increase this inertia, the only way you can increase is to decrease K1. If you want to decrease K1, the speed of the control loop goes down. So that's why I put the title of this chapter, Conflict of Inertia Response and Current Limiting. Because current limiting wants this loop to be fast. Inertia wants this loop to be slow. Right? And so you cannot make a trade-off. And basically, current limiting is very important for us. We don't want to lose it because it's a life problem for the converter, right? So we don't want to use it. And once you satisfy that, inertia that you get from the capacitor is not really anything important. It's very, very small, tiny amount. So I think I have given a simulation here. This simulation, look at very slow design. Look at this design. This design is not going to do the current limiting because the poles are negative 120. But then, if the voltage on the grid goes up and down and up, you know, these things happen because, let's say, loads are switching. So this is a good way of simulating the inertia. Increase the grid voltage, maybe linearly, and then decrease it, and then see what happens. If you increasing the voltage and the converter decreases its power, that's inertia. If you're decreasing the voltage, grid voltage, and the converter supplies power, that's inertia. But if it's the other way around, it's a destabilizing thing. So now the voltage is going up, the converter supplies less current, decreases its power. Correct. The blue one. And then again here. So it gives you some inertia. However, if you go to the faster design or faster design that we decided to go with the faster design, if you really look at this, it's not visible. If you zoom on it, you will see there is a tiny amount of reduction, but it's very small, so we cannot rely on the inertia. Okay. But then, obviously, also when a sudden voltage drop happens, if the system is very slow, you see it cannot limit the current. But the one that is fast can limit the current, no problem. So if you get current limiting, you lose inertia. If you want to have inertia, you lose the current limiting. Okay? All right. Can we solve this problem? Yes. We're going to talk about how to solve this problem. Okay, and that's this section. Can we emulate another capacitor somewhere in the control loop and emulate, not a physical capacitor? We can also have physical capacitor, but let's say now emulation. Somewhere in this control loop, which is a large capacitor, without compromising the speed of the current loop. We have to put that capacitor, virtual capacitor, outside the current loop, right? So this is the way to do it. See, the current loop is here. We do not change it because we want the current to be fast. Now I put one capacitor here, and this is a capacitor. Say set point of power minus the actual power, or you can say current, but power doesn't matter, because current is already limited. We don't need to talk about current, so you can safely go and talk about power, because our final objective is to track the power. So set point of power minus the actual power, pass it through a capacitor. Forget about this now. We do not need it. In AC system we need that, but not in DC. And this is a capacitor, because it integrates the current or power and gives you a voltage. And then this voltage subtracted from the grid voltage and then divided by R1, and you will see in a moment, and then choose that as the reference for the current and then limit that. That's it. So basically, if you look at the circuit representation of the same thing, and remember all of this is in the control. So P set comes here, minus P is going out, that goes through this capacitor. The amount of capacitor is J1 divided by Vg. And this part, the physical representation is W minus Vg is R1I. In other words, we have an internal variable W now that stands between the grid voltage and a resistor there. It's just like the internal voltage of the synchronous machine. And then this part, we already talked about that. So we added one capacitor outside the loop, so and established the relationship between the voltage of this capacitor and the grid voltage through this block. Now, if the grid voltage drops because of some load switching in, this voltage tends to drop, this voltage tends to drop, W tends to drop, capacitor supplies energy. If the voltage goes up, the capacitor absorbs energy. And this capacitor, you can choose it large. It's not going to compromise your current limiting or anything else. Okay. So here are the equations that really describes what I just said. Let's see if this works. So I'm not going to change the current control loop, the same numbers that we designed for the faster controller. And that capacitor, I choose it 3.3 millifarad, the large capacitor here, J1 over Vg, and I have Vg, so I can find J1. How much is J1? So you will find that capacitor, and R1, we choose it. That's another parameter that you need to choose, R1. That really behaves like the synchronous reactance of the synchronous machine. If you are familiar with synchronous machine, you can make correspondence between that machine and this circuit here. Okay, so this is the design. We already had it, no problem. And now look at the response. With inertia and without inertia. Without inertia is the one without this capacitor, without this newly added capacitor. And with inertia means with this newly added capacitor. And then you see, when the grid voltage starts going up in this region, the converter absorbs energy. And if it ramps up at a constant ramp, it absorbs constant power, just like synchronous machine. And during this time, that doesn't change. Again, the power goes to 0. And then when it slows down, it supplies energy during this stage. And then I applied the other one. I showed W, the signal W. This is an internal signal, just for the sake of understanding, because that signal kind of mimics or follows the grid voltage. Like I said, it's very similar to internal voltage of the synchronous machines. And here, at this point, we have a grid fault, and the current is supposed to be limited at 40, I guess. So it's limited at 40. No problem. The previous case, previous simulation, it was not able to limit that, but this one really limited that. Let's see what example was here. Okay, it's next system. Now, here we talked about emulated capacitor, right? In this example and in this discussion. This is the circuit we just discussed. If it's an actual capacitor, it's no problem either. And that actual capacitor happens when you have a two-stage converter. In a single stage, you cannot have an actual capacitor. Yes, you can have, I mean, if you put a big capacitor on the PV side. But often we do not want, for all economic reasons, to put a capacitor there. It's costly, and if it's a large capacitor, it's electrolytic capacitor, which they have reliability issues. But if you decide to have an actual capacitor there and then extract inertia from capacitor, no problem, you can do that. Let's say I put these two circuits together, and if you noticed in this presentation, all the actual hardware blocks are in gray, and control blocks are normally in blue, but if there are additional control blocks, they are in additional colors, different colors. So these are all control. These are all controls when you emulate capacitor. But here, let's say you have an actual capacitor. So the power, so there is an input power coming to this capacitor minus the output power of this capacitor, goes through the dynamic of capacitor and generates the voltage. Now measure that voltage, subtract it from or add or subtract the DC value, and then take this VG minus VG nominal rated value, and then multiply into omega gamma 1 over R1, and then that generates your reference for the current. Again, I don't know if I've shown the electrical circuit. I haven't shown electrical circuit for this one, but you can see there is a capacitor here, obviously. But what we did by this control, by this part, we linked the voltage of this capacitor to the voltage of the grid. Okay? And normally it's not a good way to directly link this voltage to that voltage. The better way is to relate the variation of this voltage around its nominal value to the variation of that voltage around its nominal value. It's a better approach. So what I have done, I took this voltage, I subtracted from the nominal value, that's the variations. I took the grid voltage, I subtracted from the nominal value, and there is a factor gamma which says how they are related with what factor. And then that goes through 1 over R1. So this R1 again plays the role of that synchronous reactance. And this I, again you can put it, it's for the rated value of the current. So this simulation, which I'm going to run for you as well on the computer, shows that if you have an actual capacitor and if you have an emulated capacitor, they behave almost perfectly the same. Right? And I will show you the circuits. This is another simulation. Let me see what's the difference between this one and this one. This basically shows both of them together. You have disturbances of the grid voltage going up and down. Like I told you, this is a very good disturbance on the grid voltage if you want to simulate or investigate the inertia response. Later on we will extend this for AC. We have current limiting, no problem, and then we have inertia response. You see the power changing all the time. When the voltage changes, the power also changes. So we have inertia response. This one here, I applied a deeper grid fault. When you apply a deeper grid fault, the voltage of the capacitor, because now the grid fault happens, it's a deep grid fault, and then you limit the current at 40, let's say for some extended time, a little bit extended time, so you cannot feed the amount of power to the grid, right? So what happens is that, and then this power coming from the initial stage. If it's two stage, it's coming from the PV, let's say, or if it's single stage, it's your set point. So the excess of power will go to the capacitor and increase the voltage of the capacitor. So you need to choose the capacitor large enough that this rise of the voltage is not going to harm your circuit. This is another indication of how to design the capacitor, if it's an actual capacitor. Now, this simulation here is an extreme case. When you reduce the capacitor very small, it's not really very important, because anyway we do not decrease the capacitor too much here because we want to have inertia, right? If you decrease it, you don't get a lot of inertia. You really get tiny amount of inertia. So inertia is very small. But what happens, oscillations start appearing on the responses. And later, I have discussed in the next little section here how you can remove these oscillations. Here, there are, you remember that parameter gamma that I said? The role of that parameter gamma is shown here, and in this diagram, the role of parameter R is shown. So gamma is the factor between the capacitor voltage and the grid voltage, right? In AC synchronous machines, grid frequency and the machine speed are the same. So there is not such a factor there. But here, because it's controlled, we can put this factor. In other words, we say, if the grid voltage changes 10 volt, now change the capacitor voltage 20 volt. It doesn't have to be equal, but just a factor. If you use that factor, and here I chose two numbers, 0.4 and 0.8, so you will get a larger amount of inertia for a smaller, compared to the other one. And this, by the way, you can use it for actual capacitor too. In other words, if you have an actual capacitor, you can use this degree of freedom to control the amount of inertia that you can get from this capacitor. But basically, just keep in mind that if you increase this factor, you are allowing the capacitor voltage to change larger. If you look at this voltage here, so for larger gamma, this capacitor voltage becomes larger. Changes on the capacitor voltage become larger, so you need to have made sure that that level of voltage can be tolerated by your circuit. Okay, and then impact of R1. R1 equal 1 is the one that we discussed in the previous simulations. Now I went to some extreme, R1 equals 0.2. I reduced the impedance, so to speak, or reactance, here in this case is resistance, between the machine and the grid. And then when you increase that reactance, and again in synchronous machines you cannot do it because it comes from the winding of the system, you cannot, there is no way to reduce that inductance or reactance. But here is a control parameters. If you decrease it, it means that you have a smaller reactance between them. So the responses become faster. If you look at this, but some oscillations appear at the response, at the transients. Okay. Now, this is the thing I said, and it's not important really practically, but it's good, it's very interesting theoretically, and you may be able to use in some of your research if you want. You see, here is the current controller we had. Then we added some virtual capacitor here. or even if it's an actual capacitor, right? So that capacitor has a new state variable. So now this system has one state variable here, one state variable here, one state variable here. If you want to have full state feedback, you need to feedback the voltage of this one, which is this variable, also into this controller. This is a full state feedback. Otherwise, it's partial feedback. Now, if you have full state feedback, all those theorems valid, and they are guaranteed. If you have partial feedback, may or may not be valid. So, but if you have full state feedback, that means now you can move the poles anywhere you want, and then you can shape the response, and you can remove the oscillations. Okay, that's basically what is done. Here I have written the equations of this circuit, and I expect that by adding this feedback loop, an additional feedback loop, I can remove the oscillations. And I applied LQT, and here is the example. So I have now 3 poles. When I increase Q, the poles move to the left. When I increase Q2 for the second one, they move down. And when I increase Q3, they move this way. Here is just to show the full picture of what is happening. Right? And then whenever you are happy with the response, with the poles, you can stop. Remember, these poles, the location of these poles tell you what is the speed of the current loop. Okay? So whenever we say, for instance, one pole is here at negative 1400 plus minus J11 to 23. One pole is at negative 1155 here. So that means you have a speed response of about 1 millisecond for the current loop. And then now you see those transients are gone, because it's full state feedback. Let me go to simulation, I think, before. Yeah, let's discuss the simulation and we'll come back here. So here you see there is a capacitor on the left side of the converter. Here there is no capacitor. It's just a battery, a voltage supply. And this capacitor obviously needs a power, right? The power should come. But we don't have power source in Simulink and in other simulation software. But we have current source. So you can put a current source here and then adjust the amount of current properly such that the amount of power that you want is coming here. So choose that current equal to the power divided by VC. So amount of power, P reference or P set point, divided by VC, that is the current, and then you apply to this controllable current source, and that means that this amount of power, P ref, will be coming from here. This is a scenario that you have 2 stages of converter. Let's say one is connected to PV, and there is a converter there which is doing maximum power point tracking. So by doing that, power is transferred or sent to the DC link. We are not talking about control of this part now. We'll talk about that later. But now from this point, from DC link, now this power is coming. We would like to have inertia from this capacitor. And obviously current limiting and everything else. This one doesn't have a capacitor. Okay. So these are the PWMs, and these are the controllers, the one that has capacitor and the one that doesn't have capacitor. The one that doesn't have a capacitor, you have to emulate it here, you see. This is the capacitor emulation block. And then the current limiting. Rest of the circuit will be the same for both of them. So this shows the currents of the two converters starting from 0, and then the set point of power is 0, and then set point goes to 3 kilowatt and then to 6 kilowatt. So two step changes, 3 kilowatt, 6 kilowatt. And then here is the disturbance on the grid happening. If you look at the grid voltage, it's going up. And this is the capacitor voltage, whether emulated or non-emulated, actual capacitor. These are the powers. See, almost the same. These minor differences, it's because we make some simplifications in the control loop. Whenever, for instance, we want to model an actual capacitor, an actual capacitor is CVV dot equals P. But normally, when you want to emulate, if you have noticed in my notes, I use C into rated value of V into V dot to make it simple. And it doesn't make big difference. You see, the level of difference is only this one. And this shows the currents. And the powers really show the inertia behavior. See? Here is the power which goes down from 6 kilowatt to 5 kilowatt. About 1 kilowatt is really large for a grid voltage changing from 300 ramping up to 350. So the rate of change, for this rate of change, within 0.05 seconds, you will get a power of about 1 kilowatt. So this seems to be reasonable, even though it's not really straightforward now to say much about inertia in DC systems. It's not common, but because I'm talking DC systems now, I'm teaching, I thought maybe let's clear it now. And then, but in AC, we know how much inertia synchronous generators provide, so we can really mimic them by the inverter exactly. So we designed the capacitor or emulated capacitor in AC to give us the same amount of inertia or more, if we want, that a synchronous generator provides. Yes. Okay.
Actually, the value of inertia, whatever you have chosen, it will give you the response accordingly.
Yeah.
It will absorb some power. It may have to release the power.
Right.
But the virtual inertia is in control itself. But the transfer of energy, whether it is consumption, absorb or delivering, it will be happening from the real system.
That's right.
From where this power, additional power, whether it is absorption and delivery.
Yeah, that's a very good question. I like this type of questions. In this one, in the case that it's single stage, remember this is a battery here. Yeah. In this one, it's capacitor. So you either have an actual capacitor that provides the inertia or a battery that provides the inertia.
So you should have a source
Oh yes.
capable of.
You emulate it, but you cannot create energy. This energy should come from somewhere. But you make sure that our control does, makes sure that we create a very nice stabilizing inertia. But that energy should come from somewhere, from a capacitor or from a battery.
Second, subsequently, if DC link is there and EV, DC link and then inverter, and inverter is providing grid support. If the inertia I have chosen very very high, so voltage is going down, it has to supply the energy.
Mm-hmm.
And if DC link is not capable, the PV is not capable, what will happen? DC link will be breaking down that time.
Yes, if the voltage goes below the limit, the protection device, protection part will shut down the converter.
The second objection is you can have a PESS to support that DC link in the tough time of the grid. So if
Yeah.
to support this virtual inertia,
Yeah.
so that time this PESS connection will be working all together to that what time DC link is going down and is
Right.
capable, so that
Right.
can support.
Right. So he's saying that we can have a small capacitor here and we can add a battery to it. That's what you're saying.
Yes, yes.
And make sure now you need now another controller for the battery to make sure that if the job of the battery is to provide inertia, the battery should detect when it starts. I haven't discussed that here. Those type of systems called hybrid systems in this context. So yes.
Because this side also,
But you need to justify why you want to do that. Is just using a battery there for the sake of inertia is better than using a larger capacitor or no?
because in AC grid, if suppose the reason is there, you want to maintain that frequency stability.
Mhm.
Because this capacitor, actual capacitor should,
Cannot
it
provide. Yeah.
cannot provide.
Right.
So for that,
If it's a double stage and you really want to provide frequency support, yes, that is a good scenario for adding that battery.
actually I was very confused that I mean I can include anything virtually. That, okay, J capacitor is this much. Then how? Where is this energy?
Yeah,
is
there should be some source of energy. Always find it. Yeah.
Thank you.
Yeah. All right, so let's go to our teaching, see how much. Now, one thing is you realized that we are changing the capacitor voltage if it's an actual capacitor or if it's emulated capacitor. But for emulated capacitor, no problem. But for actual capacitor, we are changing the voltage of the capacitor to attain inertia, right? If you don't want to attain inertia, some people in converters, even in AC, still support this idea, still, yeah, that I'm not convinced to provide inertia by my converter. And in this case, you need to tightly control the capacitor voltage. You want to tightly control the capacitor voltage in this the same controller that we had here. Just set gamma to 0, so disconnect that inertia loop that connected the capacitor voltage to the grid voltage, and then choose R1 as a small number. You get there. And then design your circuit. And then capacitor is a small because you don't want to generate inertia. And then in this case you use full state feedback because here is really the extreme case that capacitor is a small, R1 is a small. You need to have full state to have a nice smooth response. So that's basically what I have explained here. So you use full state feedback. Now this full state feedback, I'm going to explain this diagram here. If you look at this full state feedback, this gain particularly, K3 into VC, we have to do a caution here. And that caution is during the current limiting, whenever the system enters into or goes into the current limiting mode, we have to actually disable this block. Or if you disable it, the responses will be much better, especially in this case of tight control of the capacitor voltage. So I have explained that here, how to do that. So you basically detect when the system is in the current limiting mode. It's easy to detect that using the input and output of the saturation block. And then you freeze this block, and whenever you come out from the limiting, you just again release it. So I call it freeze and release. And I showed some simulation results for tight control of capacitor voltage. I showed on the same diagram the loose one and the tight one. The loose one is the one that you allow the capacitor voltage to change a lot to provide inertia. The tight one is the one that you really want the voltage does not change. You want that voltage to be exactly or very close to 400 volts. So, and the same simulation is run for both of them. The one that is loose provides inertia, however, the capacitor voltage changes. The one that is tight does not provide inertia, but the capacitor voltage is constant. In other words, what I was trying to say here is that if you really don't like to provide inertia, you can use the same controller. No problem. You need only to adjust two things. Put that gamma equals 0 and then choose R1 small. much smaller than the case that you provided inertia. Okay, now this support inertia, or I call it dynamic support, is the case that, if you notice, grid voltage ramps up or ramps down, right? So it responds to the changes of the grid voltage. In AC, in synchronous machines, it responds to the changes of frequency. But there is another grid support that we have in synchronous machines, and we can have it here, and that responds to the offset of the grid voltage with respect to the nominal value. And that is the droop term that we implement in the governor control system in synchronous generators, and we can implement it here as well. So if you want to have a static support or droop support, droop function, that is the expression, the mathematical expression. So when the grid voltage is above the nominal value, the converter must keep absorbing power, even if it's constant. So there should be some place to store this energy, right? And if it's lower, it should keep supplying. So the way to do it is this one. So you just take kV here into Vg minus Vg, and then you add it to the set point, just like this, and then use that as the reference for power, and then divide it by Vg. That is the current, saturate that current, and then this is only static support, no inertia. If you want to have both of them together, this is this one. So inertia is here, this part is inertia. But then you adjust the set point or the reference of your power by adding another droop term to it, such that it responds to the offset of the grid voltage. You can use this block or you don't use this block, doesn't matter. If the capacitor is large or the emulated capacitor is large, you don't need to use this block. But if the capacitor is very small, you better use this block. And now this example compares these two supports. This is the current loop design without K3, only K1 and K2. This is the same design that we did before. And now this diagram, I'm going to explain a little bit, shows responses of the converters without grid support, with static, dynamic, and both. So there are 4 responses on one graph. Okay, one without any support, one only with static, one only with dynamic, and one with both of them together. So the grid voltage, the disturbance of the grid voltage is happening here and here. Sorry, it's too small, probably you cannot see it well, but anyway, it ramps up and then it's constant and ramps down, and again ramps down, constant, and ramps up. And then here is the grid voltage drop happens. Sorry, this was the grid voltage. Okay, that was the other one, was the capacitor voltage. This is the grid voltage. Anyway, so the one without support is the blue one. You see, it keeps supplying the same amount of current. So the same amount of power. Sorry, the same amount of power, almost constant. The one that has dynamic or static support is the red one. So when the voltage starts dropping, the grid voltage starts going up, starts going up, it reduces the power. And then even if it's constant, keeps still supplying power. So that's the red one for the static. And the yellow one here is for dynamic. It actually does not provide power when the grid voltage does not change, only responds to the changes. And then when you add them together, that's last one here. So you can see you get a larger amount of support both during the transients and in the steady state. Because the droop term also adds some weight during transients, but mostly works during the steady state. Okay. I think that's it. Later on, when we get to next chapter, AC system, single phase and both, three phase, I will come back to inertia again and explain it more in that context. But this is basically for all for this chapter. Maybe a couple of minutes if there is any other questions. Maybe one or two. Any other? Did you? No?
Does these terms, this R1, J, they impacting the stability of our system and how we design these?
In the full state feedback design, no. Because we consider them in the design.
For example, PI controller simply output figure.
Yeah, now if you designed partially the current controller and now start playing with R1 and J arbitrarily, yeah, you may destabilize the system. But if you choose them first, R1 and J, then go and design the entire system full state feedback, you are guaranteed that it's stable.
Whether we really use these full state feedback in actual hardware implementation?
We can use it, no problem. But like I said, my recommendation is, because if you use it, there is a little inconvenience. You have to do that freeze release. My students always had difficulty in the lab implementing that freeze release type of things. And I told them, if you really want to get inertia, that means your capacitor is large, right? And then your R1 is large, your gamma is a good number. So all these numbers mean that the responses of the system are sufficiently slow, these responses of the external loop, you know, the inertia loop, that K3 is not going to really impact the response of the system. So the only case that you need to use K3 if you are pushing the system to the extremes. You are choosing very small R1, you are choosing gamma equals 0, you are choosing very small C, which means you don't care about inertia. You're not going, so and then you want to have very tight voltage across the capacitor. This is a very extreme case. In this case, I explained here, you need to go through that full state feedback and use K3. But other than that, my experience is K3, don't use it. It makes complications in implementation. Yeah. Any other questions? No? Okay, so we can stop here.